Hello and welcome. Take a look around you. The device you're watching this on, the lights in your room, the car in your driveway, the vast networks that bring us the internet, they all rely on a silent, unassuming hero of the electronic world. It's a component so fundamental, yet so often overlooked. It's called a capacitor. So, what is it? In the simplest terms, you can think of a capacitor as a tiny, specialized battery. But unlike the battery in your remote control, which releases its energy slowly and steadily, a capacitor can store up electrical energy and then release it in a sudden, powerful burst. It's the flash in your camera, the device that smooths out power in your computer's motherboard, and the component that helps tune your radio to the right station. Today, we're going to pull back the curtain and explore the very heart of this device. Using this diagram, we will build a complete understanding of how a capacitor works, piece by piece, concept by concept. By the end of this journey, you won't just know what these symbols and equations mean, you'll understand the beautiful physics behind them. This is a diagram of the most basic and classic type of capacitor, the parallel plate capacitor. The name itself gives us our first big clue. It's built around two plates that are parallel to each other. Let's start by looking at those. These two dark, flat surfaces are our conducting plates. The word conducting is T here. It means they are made from a material that allows electricity to move through it with incredible ease. Think of common metals like copper, aluminum, or silver. They are like superhighways for electric charges. The job of these plates is to act as reservoirs for electrical charge. When we connect this capacitor to a power source, like a battery, one plate will collect a buildup of positive charge, while the other plate collects an equal amount of negative charge. They sit there, facing each other, holding this separated charge and storing potential energy in the process. The two wires you see sticking out are the terminals, the points where we connect the capacitor into a larger electronic circuit. Now, how much charge can these plates hold? Well, one of the most important factors is their size. Look at the dimensions shown here. The plate has a width, labeled with the Greek letter omega, and a length, labeled L. Just like calculating the area of a tabletop, the surface area of our plate, which we call A, is simply its width multiplied by its length. So, A equals omega times L. This area is measured in square meters. Here's the first fundamental rule of capacitors: the larger the area of the plates, the more capacitance it has. Let me give you an analogy. Imagine you're trying to catch rainwater. A small cup has a small opening, a small area, and can only catch a little bit of rain. A wide bucket has a much larger area and can collect far more water. The capacitor plates are just like that. Larger plates provide more room for charge to spread out and accumulate, allowing the capacitor to store more energy. So, if an engineer needs a capacitor with a lot of storage capacity, one of the first things they'll do is design it with very large plates. The next critical dimension is the gap between these two plates. This is labeled with the letter D, representing the distance between the plates, measured in meters. This distance is incredibly important, and its effect is the opposite of the area. Think about magnets. When you bring the north and south poles of two magnets close together, the force of attraction between them becomes incredibly strong. The same principle applies here. The positive charges on one plate and the negative charges on the other are intensely attracted to each other across this gap. The closer you bring the plates together, the smaller the distance d, the stronger this attraction becomes. This powerful attraction allows the plates to pull in and hold even more charge from the circuit. So, here's our second fundamental rule: the smaller the distance between the plates, the more capacitance it has. This creates a design challenge for engineers. They want to make D as tiny as possible to maximize capacitance, but the plates can never touch. If they did, the charges would flow directly from one to the other, creating a short circuit, and the capacitor would fail. So, what do we put in that gap? This brings us to the secret ingredient, the material that fills the gap, the dielectric. In our diagram, it's this reddish-purple layer. A dielectric is an insulating material. An insulator is the exact opposite of a conductor. It's a material that does not allow electricity to flow through it. Think of rubber, glass, plastic, or ceramics. The dielectric serves two vital purposes. First, its most obvious job is to be a physical spacer. It keeps the two conducting plates separated, preventing them from touching, no matter how close they are. But its second job is where the real magic happens. Placing a dielectric material in the gap, instead of just leaving it as empty space or air, dramatically increases the capacitor's ability to store charge. It's not just a spacer, it's a performance enhancer. How does it do that? The answer lies in a property of the material called permittivity, represented by the Greek letter epsilon. The word permit is right there in the name. Permittivity is a measure of how much a material permits or supports the formation of an electric field. When our plates are charged, an invisible electric field is created in the space between them. The dielectric material responds to this field in a special way that reduces the overall voltage between the plates, which in turn allows them to store more charge. Think of it like this: imagine the space between the plates as a container. A vacuum is just an empty container. But a dielectric material is like putting a special, highly absorbent sponge into that container. For the same amount of effort, you can now pour far more charge into it because the sponge helps to soak it up and hold it. A material with a high permittivity is like a superabsorbent sponge for electric fields. To make this concept precise, scientists break down permittivity into two parts. First, we have a universal constant of nature, our ultimate reference point. This is the vacuum permittivity, labeled epsilon naught. This represents the permittivity of a perfect vacuum of pure, empty space. It's the absolute baseline for how an electric field behaves. Its value is a tiny 8.854 times 10 to the power of negative 12 farads per meter. You don't need to memorize that number, just understand its role. It's the fundamental permittivity of the universe itself. But we're not using a vacuum, are we? We're using a specific material. So, we need a way to score how good our material is compared to that baseline vacuum. That's the job of the relative permittivity, epsilon r, also known as the dielectric constant. The word relative is everything here. It tells you the permittivity of a material relative to a vacuum. It's a simple multiplier. For example, air has a relative permittivity of about 1.0006, which is so close to 1 that it's practically the same as a vacuum. But a material like glass might have a relative permittivity of 7. This means a capacitor with a glass dielectric can store 7 times more charge than the exact same capacitor with just air or a vacuum between its plates. High-tech ceramics can have relative permittivities in the thousands. Because it's just a comparative ratio, a score, it has no units. That's why the diagram says it's dimensionless. So, to find the total, or absolute permittivity, epsilon, of our chosen material, we simply take the universal baseline, epsilon naught, and multiply it by our material's unique score, its relative permittivity, epsilon r. This gives us the final, effective permittivity of the stuff we've put between our plates. And now, we can finally bring everything together. We've looked at the plates, the area, the distance, and the dielectric material. All of these concepts combine into one elegant and powerful equation that defines the capacitance, C. Capacitance is the official name for a capacitor's ability to store charge. It's measured in a unit called the farad, spelled F-A-R-A-D, named after the great scientist Michael Faraday. The formula is C equals epsilon times A, all divided by D. Let's translate this from math into words. It says, the capacitance, C, of our device is determined by the absolute permittivity, epsilon, of the dielectric material inside it, multiplied by the area, A, of the conducting plates, all divided by the distance, D, separating those plates. This single equation is a complete recipe for building a capacitor. It tells an engineer exactly what to do to get the performance they need. Want more capacitance? Use a material with a higher permittivity, a better sponge, epsilon. Want more capacitance? Make the plates bigger, increase A. Want more capacitance? Move the plates closer together, decrease D. You'll also see the formula written as C equals epsilon r times epsilon naught times A, all divided by D. This is the exact same thing. It just shows the two parts of permittivity separately, which is more practical for an engineer who is looking up the relative permittivity of a material in a handbook. So there you have it. The parallel plate capacitor, which at first glance might seem complex, is really just a story of three simple ideas. It's a sandwich of two conductive plates, whose ability to store energy is maximized by making them as large as possible, placing them as close as possible without touching, and filling the gap between them with a special insulating material that enhances the electric field. Area, distance, material. Those are the secrets. It's this beautiful and predictable relationship between geometry and physics that makes the capacitor an indispensable building block of our modern technological world. Thank you for joining us on this deep dive. We hope you now see the elegant science packed into this tiny component. Stay curious, and we'll see you next time.